Hello, I'm Yusuf Kayra Gül and I'm a physics student at Bilkent University. I want to present me and my teammates Physics 211 term project. The name of our project is Vibration Analysis of a Loudspeaker via Michelson Interferometer. As the name states, we built a modified version of so-known Michelson Interferometer to vibrate one of the mirrors with intended frequency. This vibration then also vibrated the interference pattern. We captured and analyzed this vibration with a photodiode. The mentioned modification on the interferometer done by introducing a loudspeaker to backside one of the mirrors. The experimental setup and method will be presented, but for now, let's look at the theoretical background of our experiment. The electric fields of the two interfering beams are expressed at the top, and by superposing them, we get the expression at the bottom. And since the intensity is proportional to the squared magnitude of the total electric field, we get this expression by some algebraic manipulation on exponentials. Since delta phi is the phase difference, we can express this phase difference in terms of the optical path difference. In the modified configuration used in this experiment, one mirror is fixed while the other is mounted on a loudspeaker. The oscillatory motion of the loudspeaker induces periodic displacements of the mirror and modulating the optical path difference. If the mirror undergoes sinusoidal motion, the path difference, delta d, can be expressed with this expression. This periodic modulation causes the interference fringes to oscillate, producing a harmonic variation in the output of the photodetector. We captured and analyzed this variation with our setup. So, let's see our setup. What you are seeing on the screen is a demonstration of the setup consisting of a laser, beam splitter, loudspeaker, two mirrors, and a photodetector. As you can see, the loudspeaker is placed at the back of one of the mirrors. And this is the actual setup. As you can see, we used a microscope slide as a beam splitter. The laser beam split it into two beams, then reflect back from the two perpendicularly placed mirrors, and meet back on the microscope slide. Any path difference between two beams creates the interference pattern. If you look at the mirror on the left, you can see the loudspeaker placed behind the mirror. We used it to vibrate that mirror to create an alteration in the path difference, thus in the pattern. To capture these vibrations clearly, we magnified the interference pattern using the lenses at the right. Since I presented the theory and the setup, I can now present the results. We divide our measurements into two sections: distinct frequencies and complex frequencies. We used MATLAB to create single, double, triple sine waves at different frequencies and convert them into sound. We used this sound to vibrate one of the mirrors, then capture and analyze the vibration of pattern. We categorized measurements of this kind as distinct frequency measurements. Then we used movie soundtracks, sound and music recordings to capture our data. The data then analyzed and reconstructed as sound to be compared with an original sound. We categorized measurements of this kind as complex frequency measurements. What you are seeing on the screen is now that the interference pattern we used to measure our data. This is the plot of FFT analysis of the data collected with a vibration of 400 Hz is applied. This clearly shows a peak at 400.4 Hz, which is sufficiently consistent with the introduced vibration of 400 Hz. Also, there are other peaks at integer multiples of 400 Hz caused by both convolution in FFT and harmonic distortion. And this is the plot of FFT analysis of the data collected with a vibration of 1000 Hz is applied. As you can see, there is a distinct peak at 1001 Hz, which is sufficiently consistent with the introduced vibration of 1000 Hz. The interesting thing is that both 400 Hz and 1000 Hz measurements has an error of exactly 0.1%, which is also could be a consequence of harmonic distortion or the spacing of the grid used while FFT. What you are seeing in the screen is that the plot of FFT analysis of the data collected with vibrations of 400 Hz and 600 Hz are applied simultaneously. As you can see, the highest peaks present are at 400.4 and 600.6 Hz, which are greatly consistent with the introduced vibrations of 400 and 600 Hz. Now, we moved on to triple frequencies. What you are seeing on the screen is that the plot of FFT analysis of the data collected with vibrations of 400, 600, and 1000 Hz. As you can see, there are complements of the given frequencies in the FFT plot at 400.5, 600.7, and 1001 Hz. 400.5 Hz and 600.7 Hz are clearly consequences of the vibration introduced to the system. But since 1001 Hz also appears in the previous measurement, it is not clear that if 1001 Hz is a consequence of convolution, harmonic distortion, or the actual vibration introduced to the system. Although the system should have been captured the 1000 Hz frequency as the previous measurements implies. Thus, probably the peak at 1001 Hz in this measurement is a consequence of all convolution, harmonic distortion, and actual vibration in the system. For the complex frequencies part of our experiment, sound waves of a music record have been introduced to the system via loudspeaker. The data is captured for 20 seconds and the same FFT algorithm is applied to the data. Also, an FFT has applied to the same 20 seconds of the music record introduced to the system. What you are seeing on the screen is that the comparison of the FFT analysis of our data and the actual sound. At the top, the FFT of actual sound, and at the bottom, FFT of our data. As you can see, the general shape of the experimental result is consistent with the audio reference. Nevertheless, the amplitude proportions between frequencies are slightly off due to both noise and imperfections of the FFT algorithm. Now we came to the fun part. Let's hear and compare the actual sounds and the reconstructed sounds by our system.